All right, so what we're going to do today is we're going to talk about how to use the model. And as long as I know exactly where I ended up yesterday, we should be fine for today. So at the end of yesterday, we were talking about the two different parts of Newton's law. The first law, which is net force equals 0. And the second law, which we didn't get to, is net force equals ma. And today we're going to talk about how these two things get used to solve questions. I would be remiss in my duties if I didn't at least take a moment and indicate that they are the same law. The fact that they are separated into a first law and second law is simply arbitrary to help their little feeble minds wrap around what's happening here. But that doesn't have to be true. Net force equals 0 is a statement suggesting that that system is not changing. And net force equals ma is suggesting that that system is changing. That's what these two things are about. This one applies to situations in which the velocity is a constant. And that's what we talked about yesterday. And this one applies to situations where the velocity is changing. What's most important here is that when I say which one is constant, which one's changing, most people think I'm just talking about speeding up or slowing down, but I'm not. Whenever the velocity changes, whenever the object goes faster, goes slower, or changes direction, or both, that's a change. So I could be going from 0 to 100 miles an hour. That would definitely require an unbalanced force. But I could also be going at a constant 20 miles an hour and make a left turn. That would require an unbalanced force. Vector is something that has magnitude and direction. So if the direction of the vector is changing, then we're dealing with something where there's an unbalanced force to cause that change in direction. So just be aware, these are all vector quantities. And therefore, any part of the vector that changes results in the use of the second law. Now, when you are advancing into a problem, one of the first things you'll be asked to do is to try and determine whether you feel that the problem falls under the first law or falls under the second law. Most of the times, that's obvious. But most students tend to come at the problem and think that if the object is moving, it's a second law problem. That for whatever reason, maintaining a velocity requires an unbalanced force. That is not true. Movement isn't the answer. Acceleration is the answer. Something about the movement has to be changing in order for it to be a second law problem. If I set my cruise control for 50 miles an hour, the car is going to attempt to balance the forces on the car in order for it to maintain its velocity. It doesn't mean no force. It means that everything is balanced. If I slam on the brakes, that's the unbalanced situation. So when you're asked to determine whether our situation falls into a first law problem or a second law problem, you choose it based on which one is accelerating. If you don't know, this is the default. Meaning if you don't know whether the system is going to provide an acceleration or not, you have to assume that it does until you prove that it doesn't. And that's a gray area that makes it a little bit tougher. So under those circumstances, there's probably information about force, and you will have to see if that information balances before you decide whether it's going to be a net force equals 0 or a net force equals ma problem. So you assume it accelerates until you prove otherwise. Trust me, that won't be the hardest decision you have to make. Now, in making these decisions, one of the things I'm going to ask you to do is after you've decided this, you then have to identify the forces that might be acting on your system, which might seem like there's an infinite number of possibilities. There are a lot of different forces. That part's true, but there's not an unlimited number of possibilities. But there are a lot of possibilities. So what I'm going to do next is talk about what is necessary to know in order to draw a free body diagram, which is going to be the essential part to how we solve our problems. And I did not make this clear all of the day, but I need to really drive it home since I'm recording this. A free body diagram is an essential tool. If you can't get the free body diagram right, you can't solve the problem. So those of you who have had physics before know exactly how I feel about this. Not every physics teacher does, but this is essential. It will be on every single test. There will be a box on every test that has forces for you to put your free body diagram in it. And if it's wrong, the rest of your problem is likely going to be wrong to follow. And there's really no recovery. Unlike with the other problems where you can kind of follow your ideas through to the end, if you blow the free body diagram, your ideas are going to be garbage too. So this part has to be done right. And let me also interject here and say that the whole point here is to be able to solve a problem. We are attempting to use Newton's laws to do so. And as I started yesterday, Newton's laws can solve an incredible number of questions. They are amazing at being able to do that. In fact, they are probably going to be able to solve any kind of kinematics question. Any question involving motion can likely be solved with Newton's laws. They apply in almost any circumstance. They also represent the absolute hardest way to solve any of these problems. Everything else we learn after this is about how we could get around using Newton's laws. How could we not use them? Because Newton's laws represent the most complicated way to solve any problem. At the end of Newton's laws, all you will ever be able to find out is the size of an individual force or the size of the acceleration. Period. That is all Newton's laws can tell you. I don't want to repeat that 10 times, but you novices should write that down. And you guys who are pros, it might be important for you to remember. The only thing Newton's laws can actually tell you is the size of an individual force and or the size of the acceleration. Newton's laws are about force and acceleration. Now, with acceleration, we get velocity, displacement. With force, we can find some other things out, like whether the fishing line breaks or the building can stay standing under the weight that it's having to support. So there might be other questions related to it, but Newton's laws can only tell you the size of a force or the size of the acceleration. That's all they are suited to do. Now, in talking about force, we really need to understand that there are two categories of forces. Fundamental or conservative forces, and then contact forces. I want to take a few minutes to talk about the fundamental forces. And although most of what I'm about to talk about isn't actually going to be on your test, I think it's important that you kind of have an idea of the fundamental forces. The fundamental forces are often called the fundamental interactions. And it's because they're different than other forces. They are, weird's the wrong word, they are not understood. They are a mystery. They might as well be, for all intents and purposes, they might as well be voodoo. They are completely mystery and unknown. We tend to think we have a big handle on stuff. For example, the first fundamental force, you drop your pencil, what causes it to fall? Yeah, we always have this idea that because we have a word to describe something, we somehow understand it. That's furthest from the truth. We humans love to name things, and we like to do so because it makes us feel like we have power over them. Trust me, we have no idea what's going on here. None. It is not like the pencil knows where the earth is and knows which way to fall. When you drop that pencil or you've tripped and fallen, how did you know where to go? The pencil doesn't know. It's not aware. It's not awake. Well, it might as well be magic. I know somebody's saying that hoping for a quick laugh, but it might as well be. There's not a human on earth that can tell you why the pencil falls towards the earth, because none of them know. There are theories about it. I am a field effect theorist, which means I believe the earth has created something around it that changes space, like basically makes a big dent in space and stuff falls towards it, like a big guy standing in the middle of a trampoline, little things roll in towards the big guy. That's what I think is happening. Why? Because I can put that in my imagination. I can see it in my mind, and it seems to make sense. The moon makes its own dent, not as big as the Earth's dent, it's not as big as the sun's dent, and we're all falling towards each other. I don't know if it's true or not, but I can imagine that. There are people who believe there's particle effect theorists. Particle effect theorists believe that the Earth is sending out an endless stream of graviton particles. And if you are in the region where those graviton particles are being emitted, then you will interact with those graviton particles, which will give you information about where the Earth is and how strong the force is from the Earth, and you will in turn know where to fall because you have received these particles, interacted with them, and they have caused a force between you and the Earth, a connection that exists. These graviton particles are unable to be detected, travel faster than the speed of light, are massless, tasteless, I don't know. It's crazy, but it's no crazier than thinking the Earth makes a big dent in space. I don't really have the answer here. All we know is that gravity is an attractive force between things that have gravitational mass, meaning gravity acts on gravitational mass. Not to be confused with inertial mass. There's gravitational mass and there's inertial mass. So all things with gravitational mass are pulled towards all other things with gravitational mass. We call gravitational mass an intrinsic property. I used to ask students to define the word intrinsic. I don't want to anymore. It's just an exercise in futility. It's like asking them to define what mass is that they don't really know. And that's because intrinsic properties can't be defined. You can't really define mass. You can describe mass. You can describe what it does. But generally, the descriptions of mass tend to bring up words that you also don't know the definition of. So it becomes pretty circular pretty fast. Mass is an intrinsic property. I know it when I see it. That's kind of what it comes down to. Anybody else ever have to get that pop-up thing when you put your password in that says, here, pick out the thing that's a bicycle? You know what I'm talking about? And they figure we can do that because we're humans and we've seen other bicycles before and we can select the things that are bicycles. That's kind of this, except that I can define a freaking bicycle. An intrinsic property doesn't really have description, but you know it when you see it. That's the kind of thing we're talking about here. It's like asking what is a human? Well, I can probably name a lot of properties of humans, but every time I do, somebody will say, well, I know a guy who doesn't have that. 2 arms? Well, I know a 1-armed guy. I mean, you'll get that a lot. But if you'll know a human when you see him. It's the same kind of thing here. An intrinsic property, the actual word intrinsic means to be a part of the nature of something. That's what intrinsic means. But here, that word has an additional meaning in that gravitational mass exists because gravity exists. The mass creates the gravity, and the gravity acts on the mass. All of the fundamental forces act on specific intrinsic properties. If you don't have mass, you don't experience gravity. If you have mass, you do. There are things without mass. They don't experience gravity. There's the electromagnetic force. There's the weak nuclear force. And there's the strong nuclear force. These are the 4 fundamental interactions. Gravity tends to be the one people know about, and you might know a little bit about these others. I'll tell you this, the 4 fundamental interactions all share one thing in common. They all act on a particular intrinsic property, and they are all created by that particular intrinsic property. They also all act without contact across distances. The Earth acts on the moon. They are not connected, but the Earth still pulls on it. The sun still pulls on the Earth. They act without contact. That is what all fundamental forces have in common. They act on intrinsic properties, and they act across distances without contact. Now, we call them the fundamental interactions because there's something larger happening here. You see, force is the way in which energy gets transferred from one thing to another. Force is like a connection that can transfer energy. When you understand that, you begin to understand that this is all that there is in the universe. This is where all energy comes from. And you might actually know that already. We burn gasoline as a means of generating energy. But we also run water over dams as a means of generating energy. We also allow the fission of plutonium as a means of generating energy. Each one of these is a different way of interacting with the energy locked up inside the intrinsic properties of matter. Now, this may or may not be known to you, but this is not in an arbitrary order. They go in order from weakest to strongest. If I put 100 meters high water all over Tampa and allowed it to run over a dam, that would power Tampa for about an hour. If I filled this room, though, with natural gas and burned it, that would probably power Tampa for about a day. Liquefied natural gas. But if I had that cup right there, that white one, filled with plutonium, that would power Tampa for about a year and a half. That's the range of the size of these forces. Gravity is the weakest. The strong nuclear is the strongest. Now, there are interesting things about these I want you to know, but there's just so much there's so much that we don't know that it makes this a hard conversation. For example, the electromagnetic force acts on the intrinsic property charge. You guys with chemistry or AP chemistry know a little bit about charge. You may know that the unit is the coulomb. You may know that it's something about the electron and the proton. What you probably also know about charge is that like charges repel, unlike charges attract. What makes that interesting is that the electromagnetic force is the only force that can push. It can separate things. Every other force is an attractive force. But the electromagnetic one, the only one that can both repel and attract. Nothing else in the universe repels. So if something's being pushed apart, it's the electromagnetic force because nothing else can do it. A little odd behavior. However, if you have no charge, you're invisible to the electromagnetic force. I want you to imagine you have a magnet. You can push a paperclip around with the magnet. But once you get to a piece of metal that is not magnetized or can't support a magnetic field, suddenly that piece is invisible to the magnet. Or a piece of plastic, or a piece of paper. There's neutrons. You can't pick up a neutron. You can push an electron around. You can push a proton around. But you can't push a neutron around. If you want to push a neutron around, you have to attach it to something else, move that thing around, and then detach the neutron because it's neutral. You can't pick it up with the electromagnetic force. It's invisible. Now, I have no idea what that is. None. I have been teaching physics for a long time. I was in your seats a long, long, long time ago. And when I was told that there was a weak nuclear force. My teacher, less inspired than I guess, really didn't have much to say about it. Now, when I went to college, I learned that it wasn't its own force, that these two were one force called the electroweak force, because that meant that clearly physicists decided that there was just not enough to know about that one force, so we didn't even bother. And then sometime in the last, 26 years, it became a force again. I don't really know when. Some transition in one of those textbooks decided, okay, time to break that sucker back out. We don't know any more about it, by the way. I could not tell you the intrinsic property it acts on because you wouldn't believe me if I told you. And what I know is of weak knowledge. It's weak sauce. I don't really want to go into it. But I will tell you this about it. It controls radioactive decay, which might not sound like much until you realize it can eject an entire helium atom from a uranium atom. Just pop it right out if it feels like it. It can cause a proton to become a neutron. And in so doing, eject a positively charged electron. It can do the reverse, too. It can grab an electron, shove it inside a proton, and turn it into a neutron. It can do some weird things. We know that it has a desire to want to balance the number of neutrons and protons. But as a force goes, I really have no idea what it is. None. But I can tell you that the strong nuclear force acts on nucleons. That's its intrinsic property. Nucleons. And nucleons is a fun word because it really means something that lives in the nucleus. The truth is it acts on something called hadrons, but you don't know what that is probably, so I don't really want to go into it. But a hadron for you guys is a proton or a neutron. It pulls them together. It binds the nucleus together. I would love for it to be that simple, though. There must be something going on there. Like I said, this whole thing's a mystery. Meaning a proton and proton, nope, won't do it. Proton, neutron, fine. They'll do it. They'll form a nucleus. Proton, neutron, yep, no problem. Proton, neutron, nope, ain't gonna happen. Proton, neutron, fine. Really powerful. Good, strong one. That's helium. Proton, neutron. Okay, for a little while. And then suddenly the proton turns into a neutron and it's proton, neutron. I don't know why. I guess the one combination was okay and the other one wasn't. I don't know what, some kind of orgy going on there. Decided, well, that wouldn't work for us. So we're going to try something different. It's a whole mad world out there, and I can't figure it out. And nobody really can. I mean, we do know one thing that's a little bit odd about this whole little thing going on at the center there, that they're not happy with themselves unless they balance things out just right. The problem is that we have these odd number ones, and they really don't know what to do. You guys learned in chemistry, right? When you watched, from hydrogen to iron. the number of protons and neutrons is almost equal every time. But of course, if you have an atomic number that's odd, then you're going to, atomic mass that's odd, then you're going to have one more neutron or one less neutron than you do protons. And that's where the wiggle room comes in, so to speak. After iron, that's not true. After iron, the number of neutrons needed for a stable nucleus increases rapidly, which is why you get something like plutonium, which can have 240 nucleons, but only 92 of them are protons. The rest are all neutrons. So there's a lot more neutrons than there are protons then. We don't really know why. So I don't know what kind of party's going on inside there, but it's complicated. Probably don't want to know. The fundamental forces are very, very interesting is the wrong word. And fundamental, I've already used it. But they are what operates the universe. The contact forces are just the results of the fundamental forces. But this is what's really going on, and we have no idea what that is. But again, 3 things I want you to know. They act on intrinsic properties. Each one has its own unique intrinsic property. That property creates that force and is bound by that force. So mass creates the force of gravity and is bound by the force of gravity. Charge creates the electromagnetic force and is bound by that force. The nucleons, they're just having a party. Don't really know. Now, in addition to that, they're in order of weakest to strongest. I want you to know that too. Gravity is the weakest, strong nuclear is the strongest. This is also the order of their range, but it's the opposite. Gravity has the longest range, strong nuclear has the shortest range. We can experience gravitational waves from other galaxies. The strong nuclear force is about 1 times 10 to the negative 10th meters. About 2 femtometers. There it is, 10 to the negative 15th meters. That's about the size of the strong nuclear force. So there's a lot of different range there. So although this is an order of increasing power, it's an order of decreasing range. And the last thing, and the most important, they act without contact across distances. Strong nuclear force acts across a very small distance, but still acts without contact across distances. In this class, though, for the time being, only one of these matters. And that is your weight. We call the force of gravity weight. And I will use a capital W for weight. And in addition to that, the weight of an object is the unbalanced force of gravity that acts on an object. So if I drop an object, the weight of that object would equal ma, where a is the acceleration of the object. Near the Earth or near any planet or moon, the object's weight would then be mg, where g is the acceleration of gravity near that object. This is how we compute the weight of an object, mg, where this m represents the gravitational mass. We're going to come back to the difference between that and inertial mass, but that's later. So now that that's out of the way, let's get to the things that you really, really need here. Contact forces. All of the rest of the forces are technically contact forces, but we're going to still separate them into smaller distinctions so they're easier to understand. Now, the intrinsic properties, the intrinsic forces, the fundamental forces, they act without contact. They act in an odd way. But in the 3rd grade, 2nd grade, probably 1st grade, you had a good idea or a good handle on what a force is. What is the 3rd grade definition of force? Push or pull, that's right. So we have 2 kinds of contact forces, pushing forces and pulling forces. Literally that simple. But we call pushing forces in physics normal forces. And they are called normal not because they are ordinary. They are called normal because they are, by definition, perpendicular to the surface in contact. Which means right now there's a force on the pen that you're holding that is upwards because it is perpendicular to the table. There might be a force on your back if you're leaning back that's forwards because it has to be perpendicular to the surface of the chair. Your feet are probably experiencing an upward force because they are against the floor, and that's perpendicular to the surface of the floor. And it's really fun to watch all of you shift as I say those things, as if you are testing the floor and the back of your chair, you morons. I mean, you interesting young people. It's important that you understand that you don't get to choose this direction. If you are standing on a ramp, the force on you is not up. It is in the direction perpendicular to the ramp. So when we apply Newton's laws and you are looking at a situation, you must understand that the normal force must be perpendicular to the surface regardless of the direction of that surface. If you lean against the wall pushes perpendicular to the wall. So a wall can't hold you up. You understand what I mean by that? It can only push sideways. Now, that being said, pulling forces are tension forces. Use a capital T there. I think this is obvious, but pulling forces have to be in any direction away from the object. Any direction away from the object. Generally, a tension force is going to imply a cable, a string, a rope, your arm, a handle, because the tension force is going to be in the direction of that string, rope, arm, or handle. When you pull on something, you form a conduit to the object. The direction of the force is in the direction of that conduit. So they can be in any direction, but they have to be away from the object. You can't push a rope. Therefore, you can't have a force that pushes using tension. Only pulls. I think that's obvious, but there's people who have never used a rope before. Put that over here a little bit, and let's make a little extra room at the bottom for resistive forces. Now, there's only two more forces that we're really going to have in this list. There are other forces. We just don't talk about them much in this class. The resistive forces, by name, should be obvious. They are attempting to prevent motion. They're attempting to impede motion. That doesn't mean that there has to be motion. They are attempting to prevent motion. The first is friction. I'll use a lowercase f for friction. Friction is a force that attempts to prevent one surface sliding past another. I'm going to say that again because I'm not writing that down. Friction is a force that attempts to prevent one surface from sliding past another. I'm saying attempts to prevent because there are two types of friction. Again, friction is a force that attempts to prevent one surface from sliding past another. Got it? I know I'm going fast, but I don't care. You can write. There are two kinds of frictional force, static and kinetic. I'm pretty sure you can pick out which one of these occurs when an object isn't moving and which one occurs when an object is moving. But if not, then you're in the wrong classroom. So friction can exist to hold something in place, but friction can also act to slow something down or to try and prevent something from sliding, even if it already is. Now, the last one is drag. And I don't have any special letters here. And I'm going to stop here and tell you that your textbook does not use these symbols. Your textbook is going to do things like F of W for weight, or F of G for weight, and F of N for normal, and F of T for tension. And I am not going to do that. Because what if you have two tensions? You have FT1 and FT2? I don't think so. What if there's two objects, each is experiencing two forms of tension? Do you really want to do that? I really don't. So I don't use subscripts like that. I will just use subscripts for numbering forces, but I will use the capital letter of the name of each force. So W, N, T, F, that's all fine. But with drag, I don't use a D, and there's reasons why. We don't have drag very often. Drag is a resistive force that resists the motion of an object through a fluid. Drag is a resistive force that resists the motion of an object through a fluid. So I have to say it again. It's a resistive force that resists the motion of an object through a fluid. It's interesting in that it is proportional. Proportional to velocity. The faster you go, the stronger this force is. But it's always in the opposite direction of velocity. So it's interesting. You throw a ball up, drag is down while the ball is going up, but it's up on the way down. Which means the ball takes longer to go up than come down. No, longer to go down. Shorter to go up than come down. That's right. That's what I meant to say. Tried it. I blew it. But it is proportional to velocity. That also makes it kind of interesting mathematically. Since net force is about acceleration, and acceleration is the derivative of velocity, it means that drag problems can be interesting mathematically because they produce problems where the velocity is changing as the acceleration is changing. They are interesting mathematically. We'll deal with them last because they will produce interesting math. That means for you guys usually confusing math. I like to think of it as interesting math. Air resistance, going through water, those are all forms of drag. But there are other forces. We have these basically form all the forces we're going to talk about in here. But there are lots of other forces in nature that we haven't talked about. Buoyancy, the thing that buoys you up, like a helium balloon is feeling a buoyant force, or you in the water feel a buoyant force. There's Bernoulli force, which has to deal with air pressures. That one is another force. There are lots of other forces that aren't in this list. Trust me, this is enough. In fact, we're going to do our first example now in 6 minutes. So it's going to be a short example, but we're going to go through all of these in the 6 minutes. So to do that, I'm going to have a demonstration, and it's a stupid, simple demonstration, but it's going to involve let's see, is my book on the table? Yep. So what I need is a calculator. What I want you to do is to draw a free body diagram. We have decided this is a first law problem, but we are going to draw a free body diagram, which means take your object and represent it as a single dot. That's step one in a free body diagram. Now, the next couple of steps are going to be drawing arrows, and each arrow is drawn specific to the force that it's supposed to be representing. However, when you're doing this, all arrows start from the dot and are outwards. Okay, it's not like tip to tail like it was when we were adding vectors together. A free body diagram, all the arrows start from the dot and face outwards. So the first force we're going to draw is probably going to be the easiest. We're going to go through this list and ask which ones of these forces apply in this situation. And trust me, when I ask, are there any fundamental forces on the object? If you want to be the smart person, just say yes, gravity. Be the first one to say it so you can sound smart, even if you don't know anything, because it's going to be on every one of these. Generally, that's not the hard one. What's hard is understanding that gravity sets the scale, meaning the size of this arrow sets the scale for all the other arrows you draw. Because forces are vectors. They have size and direction. So the size of the arrow you draw will be graded. Not by itself, but in comparison to the other arrows you're going to have to draw. Now, in the beginning, we won't be very critical of this, but we will become more critical over time. Now, once we've handled the fundamental force, it's time to go into the contact forces. Is there anything touching the calculator? Pretty sure. Yeah, the book. Right? Wasn't the book touching the calculator? That would have to be a normal force. It is a surface in contact with the calculator. In order to draw that, remember the surface was angled. So I want to draw an arrow that is perpendicular to the surface. So I've kind of lined up my arrow perpendicular to the surface, and I will move it over there so that it is lined up in the direction of the surface. It is not upwards. It is upwards and to the left, because that was the direction of the surface. Label it N. Now, was there any cables, ropes, strings tied to the calculator? No, but this does not look balanced. If these two things were pulling on the object would probably go this way. That doesn't look like it's balanced. It looks like there's some that's up and some to the left, so it's going to move generally to the left and down. There must be another force holding it in place. What do you think that force was? It's very likely it was friction. Now, friction acts to oppose motion. The only direction that the object could have traveled would have been along the ramp, either this way or this way. It's the only way it could have moved. So remember, friction opposes one surface sliding past another. Seems not unreasonable then that would have to be the direction of friction. And there's an obvious consequence here, and it's worth writing down. Friction and normal force have to be perpendicular to each other. They have to be. There's no exceptions. And listen closely, you can have a normal force without a frictional force, a slippery surface. But you can't have a frictional force without a normal force. There has to be contact with the surface for there to be friction. So if there's a frictional force, there's a normal force that caused it. Friction and normal are related. Now, we are on our last minute. And the next thing you have to do is, after you've decided that all of the forces have been identified, you're done drawing your free body diagram. But now you have to apply a coordinate system, the most misunderstood part of this. You can apply any x and y axis you want, but some are better choices than others. I want you to write this down. I don't care if the bell rings. These are your two choices on how to draw this. I'll wait for Adam. We're still going to finish. Your first priority is to line up the x-axis with the acceleration or the motion. That is your first priority. To line up the x-axis with the acceleration or the motion. So if you're drawing a coordinate system, you use that as your first priority. This object's not moving, but that's still your first priority, to line up the x-axis with the direction of motion. Your second priority, if you can't do that, is to line it up with as many forces as possible. That's your second priority. So in this instance, the best choice would be to line it up so that the x-axis is aligned with friction, because that would force the y-axis to be aligned with the normal force, and at least two of them are on your coordinate system. Trust me, you want as many lined up as possible, because any of them that are not lined up requires trig. So the more you can eliminate trig, the easier it will be for you. All right.